Hello everyone, Kodongwane, the native God here. So today we'll be looking at a problem based on epicyclic gears, which is module 1 in Mechanotechnics N5, right? If you're tuning in for the first time, please like and subscribe, as I'll be posting more content which will be helpful to you, right? If you're coming back for a second or third time, or if you've been around for a while, thank you for coming back. Like the content, also subscribe to the channel, right? Now, epicyclic gear train problems, right? We always use a table, right? We always use a table, which I'll draw for this one as well, right? But we always use a table to lay out our information and use it as we need it, right? Now, if you need to pause the video to read the statements, you can do so. But as far as how this problem will look like, as far as the front view perspective of the diagram, right? Since we haven't been given a diagram, I decided to draw it myself, right? Just a rough schematic of how this would look like from a front view perspective, right? From a front view perspective. So, like I said, if you need to pause the video and read the statement, you can do so. But what you will get from the statement, right, is that we have an analysis gear, right? And then meshing with the analysis, you have the two planetary gears. So you have this gear as well as this gear, both being the planetary gears, and then between them you have, of course, the sun gear, right? Now if you notice here, we have the number of teeth of the planet as well as the number of teeth of the sun, but we don't have the number of teeth of the annulus, right? But the one thing we do know, since we're looking at a typical epicyclic gear train, right, in which we have the annulus, the planet, as well as the sun gear, we know that the PCD of the annulus, right, we can get by adding up the gears, right, inside of the ring gear or annulus gear. So meaning the PCD of the annulus is actually equal to what? Even if you look at this schematic here, right, you can get an idea of what the PCD of the annulus is going to be equal to, right? It's going to be equal to the PCD of the planet plus the PCD of the sun, and then plus the PCD of the planet again. So this essentially is equal to, so since we have two planetary gears, it means you're going to have 2 times the PCD of the planet plus what? Plus the PCD of the sun gear, right? Now we can further simplify this by using what? The formula of the PCD. We know the PCD is equal to what? Module is equal to the module times number of teeth of A, which is equal to, so 2 times the module times number of teeth of the planet plus the module times the number of teeth of the sun. Now when looking at epicyclic gear problems, right, the module of all the gears tends to be the same, right? So meaning, since the module is the same, means that and that and that is going to cancel, and essentially you're left with number of teeth of the annulus is equal to 2 times the number of teeth of the planet plus the number of teeth of the sun here, right? We can now use this relationship in calculating any of the number of teeth in a typical epicyclic gear system which we might need, right? So in this case, we have the number of teeth of the planet as well as the sun gear, so we can use this relationship to get the number of teeth of the annulus, right? So now teeth of the annulus is equal to 2 times number of teeth of the planet is 40, so you have 40 plus the number of teeth of the sun, which is 20. And if you plug this in your calculators, you're going to get 100 number of teeth. So the number of teeth of the annulus is 100 teeth, right? Now it is very important that you have all the number of teeth of your gears, because it is important for condition 1 in our table. Right, so remember, like I mentioned earlier, for any and all problems based on epicyclic gear trains, we need to draw up a table in which we can lay out all the information. Right, now I already have a template of the table. Right, I'll just edit this one. Right, so our table will look like this one, where we have, right, we have the condition, right, and then we have each column is, we're going to have some apparatus of the planetary gear system. So we're going to have an arm, and then we're going to have a column for the annulus, the planet gear, as well as the sun gear. Right, now it is also very important to check the sub questions of your question, right, just in case you're going to have more than one condition after the first and second condition. Right, remember, again, in your table, the first as well as the second condition, so the first as well as your second condition, right, are fixed, meaning they don't change. Right, the first condition being we fix the arm and rotates the annulus by 1 revolution clockwise. Right, then the second condition, you multiply the first condition by x and you add y. Subsequent conditions after the second condition, right, are going to be based on the kind of questions or the number of questions that we have based on the problem we're looking at. So in this case, if you look at the sub questions, so from 1.1 to 1.3, right, if you look at 1.1 and 1.3, right, both of those sub questions are going to require us to have so meaning 2 more conditions. So the 1.1 is basically going to become our third condition in the table. Then 1.3 is going to become the fourth condition in our table. And the reason why it is important for you to check that before drawing up your table or labeling or filling your table, right, is so that you make sure that your table is enough for 4 conditions. Right, so we're going to extend our table so that it suits 4 conditions. Right, right, and of course let's close this out. Right, and then this will be for our fourth condition. Right, now the first condition, the reason why it is important to make sure that you have all the number of teeth, right, because in the first condition, all we really need from the statement is the number of teeth. If you have all the number of teeth, then you can successfully complete the first condition. Right, now out of all these conditions, condition 1 is probably the most important. Right, if you mess up the first condition, then it's basically over, because all the other conditions are contingent on us getting the first condition correctly. Right, so what I like to do is to fill in all the number of teeth at the top of each column. Right, so we're going to have our annulus said it's gear A, so we're going to have gear A here for the annulus, and then we're going to have gear P for the planet, and we're going to have the sun gear. Right, now the number of teeth of the annulus is 100 number of teeth, then we have 40 teeth here, then for the sun you have 20 teeth. Right, so first condition, right, first condition, we fix the arm. The arm hasn't been named by any letter specifically, so we're just going to use arm as it is. So we fix arm and rotate. So our annulus is gear A, so we're going to rotate gear A by 1 revolution clockwise. The plus 1 rev is shorthand for by 1 revolution clockwise. Right, now since the arm is fixed, it's obviously equal to 0, and from the first condition, gear A is being rotated by 1 revolution clockwise. So the rotational frequency of A is 1 revolution clockwise, right, or 1 revolution per minute. Right, Now we look at how this affects the rotational frequency of the other gears. So if the arm is fixed and gear A is being rotated by 1 revolution, right, what then becomes of the rotational frequency of gear P as well as gear S, right? So the best way to solve that, right, the best way to come up with the rotational frequency of the other gears, right, is by first establishing a relationship of the gear you're looking at with the gear that it is meshing with, right? So if we look here, the planetary gear, so gear P, it's meshing with both the annulus and the sun gear. But because we have the most information with the annulus, right, we're going to establish a relationship between the planetary gear as well as the annulus, right? By establishing a relationship, I mean, we know that between meshing gears, right? Between meshing gears, we know that the circumferential velocities of both gears is the same, right? So meaning what? So meaning, since we're looking at gear P and gear A, it means VA is equal to what? VP, right? And what is this equal to? This will come down to NA times TA being equal to what? NP times TP, right? So this here is the relationship between the two gears. So by you first establish the relationship between two gears, right? This is what I mean, right? So this is the relationship. Then what you do next is establish the direction of both gears, right? Now, from the first condition, right, we've already established that gear A is rotating clockwise, right? Now gear P is meshing with the annulus or ring gear. Now, if you're looking at an annulus and the annulus has inside teeth, whichever gear that meshes with the annulus tends to go in the same direction as the annulus, but only if you're looking at a gear that's meshing with the annulus and the annulus is using its internal teeth, right? So for a gear that meshes with the annulus using its internal teeth, right, that gear tends to go in the same direction as the annulus, or vice versa, right? So we've already established that gear A, the annulus, is going clockwise, meaning the planetary gear is also going to go clockwise. So both are going to remain positive, right? Remember, as far as direction, if the gear is going clockwise, then it remains positive. But if it's going anti-clockwise, then we say it is negative, right? So dividing this, remember we are looking for NP, right? The rotational frequency of the planet. So you divide both sides by what? By TP, right? So essentially, NP is equal to what? NA times TA over what? Over TP, right? Now let's fill this in our table, right? Now I've already established that NA times TA over TP is equal to what's the rotational frequency of the planet gear. So this is equal to NA being what? Being positive 1, right? Remember, from the first condition, we've already established that gear A, which is the annulus, is rotating by 1 revolution per minute, essentially. So you have 1 times TA, which is what? 100, over what? Over TP, which is 40, right? Now, if you punch this in your calculators, you're going to get 2.5, right? Now we do the same thing with gear S, right? Establish a relationship between it and the gear it's meshing with, then establish the direction of both gears, and then we do the substitution, right? Now we know the sun gear is meshing with the planetary gear, right? So essentially, the relationship between the two gears is what? Is one of the circumferential velocity, which is NS times TS is equal to NP times TP. Because the gears are meshing, the circumferential velocities are the same, right? So this is the relationship we've established between the two gears. Next, you establish the direction of both gears. We already know that the planetary gear is going or is rotating clockwise. Now, the planetary gear, right, as well as the sun gear, have teeth on the outside true circumference, right? Meaning what? Meaning they are meshing with the outside true circumference, and because they are meshing with the outside true circumference, it means they are rotating in different directions, right? So taking that into consideration, and also the fact that the planetary gear is rotating clockwise, it means the sun gear, since it has to, or since it is going in an opposite direction as to the planetary gear, it means it is going anti-clockwise, right? So again, you first establish the relationship, right? Then you establish the direction of both gears. Now we're going to solve for the rotational frequency of the sun gear. So we're going to divide both sides by what? By negative TS. So negative TS. So that cancels, meaning NS is equal to what? NP times TP over what? Over negative TS. Right? Right, so it means the rotational frequency of S is actually NP times TP over what? Over negative TS. Now we've already calculated the rotational frequency of P. We got what? We got 2,5, right? So we have the 2,5 times TP, which is 40. So we have 40 here over what? Okay, I'm losing space here. So let's do this instead. Right, so this will be equal to 2,5 times TP, which is 40 over what? Over negative TS. So negative TS being 20, so negative 20, right? Now if you punch this in your calculators, you're going to get negative 5, right? So negative 5, right? And that is our first condition complete. So our first condition is complete, and first condition is probably the most important one, so you must always make sure that you get the first condition correctly, right? Now second condition, you multiply the first condition by x and you add y, right? So 0 times x is 0, then you add y. X times 1 is x, then you add y. So 2,5 times x is 2,5x, then you add y. Minus 5 times x is minus 5x, then you add y. Second condition complete as well. We are now going to look at the statements and the questions that follow for us to be able to fill condition 3 and condition 4, right? Now whatever assumption that you've been given in your statement, we are now going to use as part of our what? Of our condition 3 as well as condition 4, right? Now we use the assumptions which we've been given in the statement as they are, unless in a question it's been stipulated otherwise, right? Now for instance, if you read our statement, right, they said an Epicyclic gear train has a sun wheel of 20 teeth and 2 planet wheels of 40 teeth each, the latter meshing with internal teeth of the fixed annulus. So the annulus is fixed. That's one of the assumptions we can get from the statement, right? The input shaft carrying the sun will transmit 4 kilowatts at what? At 200 revs per minute. So the sun gear essentially, right? They said the input shaft which is carrying the sun gear is rotating at 200 revs per minute. The input shaft is rotating at 200 revs per minute. It means the sun gear is also rotating at 300 revs per minute. So that's the second assumption we've been given in the statement, right? Now they say the output shaft is connected to an arm that carries the planet wheels, right? Remember that for us to get what we are looking for, we need at least 2 assumptions, right? So we can get so we can establish equations which will then solve simultaneously, right? So now let's look at 1.1. They said calculate the speed of the output shaft. Now the output shaft is connected to what? To the arm, right? So essentially they want us to calculate the rotational frequency of the arm, right? So the two assumptions we get from the statement is that the annulus is fixed and that the sun is rotating at positive, so 300 revolves per minute clockwise. And from 1.1 we know we need to calculate the rotational frequency as well as the direction of the arm, right? So as far as condition 3, right? As far as condition 3, they said the annulus is fixed, the annulus being A is equal to 0, right? They said the sun, so NS is what? Is positive 300 for 300 revs per minute clockwise. And they want us to calculate the rotational frequency of the output. The output is carrying the arm, therefore we're looking for the rotational frequency of the arm. So this is what you're looking for. So that completes our third condition. So we are looking for rotational frequency of the arm, right? They said the annulus is fixed. They said nothing about the planetary gears, so we leave that, and then we have the rotational frequency of the sun gear, right? Now what we do next is we equate the condition we are on with what? With condition 2 to establish what? To establish equations which will then solve simultaneously. So again, you equate condition 2 with what? With your current condition. Our current condition being what? Being condition 3. So we're going to equate y to what? To the third condition. So y essentially, so y is equal to what? Is equal to this here. Take this as our first equation, right? And then our second equation, x plus y is equal to 0. So x plus y is equal to 0. Take that as our second equation, right? Then negative 5 x plus y, so we have negative 5x plus y, right, is equal to what? Is equal to positive 300. And then we're going to take this as our third equation, right? We are looking for the rotational frequency of the arm. In order for us to get that, we need to get the value of y, right? Now the easiest way to do that is if from equation 2 and 3, right, we need to express x in terms of y, so that in one of these equations we can only have y as the only unknown, right? So let's take equation 2 and express x in terms of y. So we're going to have x is equal to, then you transpose y, negative y, take that as the fourth equation. So now you're going to substitute the fourth equation into the third equation, right? So we have minus 5x, x is equal to what? Minus y, plus y is equal to what? 300. Now negative 5 times negative y, right, is equal to what? Positive 5y, plus the y is going to give us 6y is equal to 300. Solving for y, you need to divide both sides by what? By 6. That goes. Now if you punch that in your calculators, you're going to get y as being equal to, so y is equal to what? Is equal to 50, right? Now we can say, therefore the end arm, which you know is equal to y, is essentially equal to what? So 50 revs per minute. Since it's positive, it means going clockwise, right? So that's our first, so that's the first question. So 1.1 complete. The one that has to calculate the speed and output of the output shaft, which we have, right? So now let's look at 1.2. They say calculate the torque transmitted if the overall efficiency is 95%, right? Calculate the torque transmitted if the overall efficiency is 95%, right? So that is out of 6 marks. Now there's a number of ways you can do this, right? There's a number of ways you can do this, but based on the marks for this sub question, right, you're going to take one that is, I would say, a bit longer, right, because of the marks allocated, right? So if you look here, I said the input shaft is carrying the sun gear. So we know we have the rotational frequency as well as the input power, right, of the gear system, which is what, 4 kilowatts, right? So we have the input power, we have the rotational frequency of the input, right, of the input shaft, so we can get the torque of the input as well by using what? By using the formula for power, right? By using the formula for power. So we're looking at 1.2. Remember, power, so power in is equal to what? 2 pi n in times what? Times T in. Now, the rotational frequency is in revs per minute, so we have to divide this by what? By 60, right? And then we have the power in, we have the rotational frequency of the input shaft, so we can get your what? The torque in, or the torque of the input shaft, right? So solving for T in, we get T in is equal to what? 60 times the power in over what? Over 2 pi times n in, right? So n in is essentially ns, right? So we have 60 times the power in, remember, is equal to what? 4 kilowatts. So 4 times 1,000 over what? Over 2 pi times n in. Remember, n in was equal to what? 300 revs per minute. If you punch this in your calculators, you are going to get 127, what? 324 Newton meters, right? So we have the torque in, right? We are now going to calculate the transmitted torque, which is what? Is the torque out, right? The simplest way we can do this, looking at what we have, right, and looking at the marks that have been that have been given for this, allocated for this question, right? We are going to use one of the conditions of equilibrium, right? Remember, for epicyclic gear trains, we have 2 conditions of equilibrium, right? One condition is based on the sum of torque, the sum of torques being equal to 0, right? So this one where you have T in plus torque of the output plus torque of or the braking torque, right, of the system, which will be equal to what? To 0. So that's one of the conditions of equilibrium, right? The other condition of equilibrium, because we can't use this one since there's too many unknowns. We don't know the torque out and we don't know the braking torque, right? And as such, we are going to look into whether or not we can use the other condition of equilibrium, which is equal to what? Which is equal to, so torque in times n in, so the rotational frequency of the input, right? Remember, you've been given the efficiency, right? They said the efficiency of the gear system is what? Is 95%, right? Now, if you look at the efficiency, right? If you have the efficiency of anything, right? The efficiency of anything is equal to what? Is equal to out over in, right? So when looking at just torque, right? When looking at torque, this will be equal to torque out over torque in, right? So if you were to cross multiply, the efficiency would multiply what? Torque in, hence torque out would essentially be equal to what? the efficiency times torque in, right? So we use this to establish which torque between torque out and torque in would multiply the efficiency. So from this, we've established that the efficiency would multiply the torque in. So instead of having to use the formula for efficiency, we can simply just look at this relationship which we've just established, that efficiency would multiply torque in. Therefore, in this condition of equilibrium, since we have efficiency, or since the gear system is not 100% efficient, we are going to multiply T in by the efficiency. So multiply by the efficiency, right? Plus torque out times N out, right? Plus the braking torque times essentially the rotational frequency of the gear that is being held, right, which is essentially equal to 0, right? Now remember, this condition of equilibrium is based on the fact that since the gear system is in equilibrium, it means the addition or the change in kinetic energy is also equal to 0, right? So this is where this comes from, right? Now, if you look at this one, we have T in and we have N in, we have the efficiency as well, right? We are looking for T out, we have the rotational frequency of the output shaft. Remember, we calculated we calculated the rotational frequency of the arm, and we know the arm is being carried by the output shaft. So essentially we have the rotational frequency of the of the output shaft, right? And then we don't have the braking torque, but we know that the rotational frequency of the gear that's being held is equal to 0. So essentially this here will be equal to 0. So we can use this condition of equilibrium to get torque out, right? Now, it is important to note that the input shaft, right, the input shaft is going in a clockwise direction. The output shaft is also going in a clockwise direction. Now, what does this tell us regarding the directions of the torque in and torque out? Because the input and output are going in the same direction, it means the input torque as well as output torque are going to go in different directions, right? Now, the input torque is always going in a clockwise direction, so that then means that the torque out is going to go, or you would expect, or we expect that the torque out is going to go in a negative direction or in an anti-clockwise direction. So we already expect that whichever answer we get for torque out, we expect it to be negative. So if it happens to be positive, then it means you have done something wrong somewhere, right? Right. Now, torque in is equal to what? Torque in is 127, 324 times N in, which is 300, times the efficiency, which is 95%, which is 0.95, right? Plus the torque out times N out, which was 50 revs per minute. So we have 50, right? And then this essentially is equal to 0. So that's equal to 0, right? So now we are going to transpose this here, right? Take it to the other side, and we have minus 50 T out is equal to, and if you punch this here into your calculators, right, you are going to get 36287.34, right? And then solving for T out, we have to divide both sides by what? By 50. So divide by negative 50, divide by negative 50. So T out is going to be equal to what? And if you punch this in your calculators, you're going to get 725. So negative 725, 747, right? Which essentially means you have 725, 747 Newton meters, right? And that becomes the transmitted torque which they wanted us to calculate. So the transmitted torque, which is torque out, is equal to 725, 747 Newton meters anti-clockwise. So anti-clockwise, since it's negative, right? I hope that was clear. I hope that was straightforward, right? Now let's look at the last question. Last question is, so 1.3, if the annulus is rotated independently, what should its speed be to make the output shaft rotate at 10 reps per minute, right? So remember, initially we were told that the annulus is what is fixed. They told us that the annulus was fixed, and now they're saying it is rotating, right? So we are now going to ignore the first assumption, which was that the annulus is fixed, right? So now we're going to ignore this assumption, right? They said the annulus is now rotating and the output shaft is now rotating at 10 reps per minute, so clockwise, but the input shaft is still rotating at 200 reps per minute. So our fourth condition, right? Our fourth condition is we are looking for the rotational frequency of the annulus, right? If the output shaft, right? So the output shaft is rotating at 10 reps per minute. We know the output shaft is carrying the arm. So it means an arm is equal to what? Positive 10. And then of course the input shaft, which carries the sun gear, is still rotating at 200 reps per minute clockwise, right? So the arm is now plus 10. We are looking for NA, right? And NS is still positive 300, right? So we are now going to what? Equate the second condition with our current condition. The current condition being what? Being condition 4, right? So y is going to be equal to 10. Okay, let's do this here. So let's say this is 1.3, right? Now we are going to equate the second condition to the current condition, which is the fourth condition. So y is equal to 10. So we have y is equal to 10. Take this as your first equation. Then x plus y is equal to NA. So x plus y is equal to NA. Take that as your second equation. Then negative 5, right? Negative 5 times y is equal to what? Is equal to 300. So it's equal to 300. Take this as a third equation, right? Now in order for us to get NA, right, we have to have the value of x as well as the value of y. We already have the value of y, so now we just need to get the value of x by substituting. So you're going to sub equation 1 into the third equation, right? So we have minus 5x plus y is positive 10, is equal to 300, right? Then you can take the 10 and transpose it to the other side. You're going to have minus 5x is equal to 300 minus the 10, right? Solving for x, we have to divide both sides by what? By negative 5. And the value of x then becomes what? So minus 58. So if you punch that in your calculators, you should get the minus 58, right? So now to get NA, right, NA is equal to what? X plus Y, right? Yes, so plus Y. X is equal to minus 58. Y is equal to positive 10. And here you get minus 48, right? So that means NA is actually equal to 48 revs per minute. Since it was negative, it means it's going anti-clockwise, right? It means it's going anti-clockwise, right? I hope you found this video helpful, right? It might be a bit longer than most, right? But it was important for you to see how you would attempt a question like this one, right? For other videos, if I notice that the video might be too long, what I will do is I will make 2 videos to cut down on the time for the one video, right? So in the subsequent videos, if I think it's going to be too long, what I'll do is I'll just record the one question and then record another video for a different question, right? Hope you find this video helpful, right? So remember to like and subscribe. Thank you.